Hello, students. This is the last of the screencasts on the proof that there are only four isometries. And last time in week 12, day one, we went through two reflections. It was one, two, or three reflections. We proved that every isometry is a composition of one, two, or three reflections. And we went through one and two early on, and then last time we did this transversal. The cases of two of the lines are parallel, and one is a transversal. And this first case was transversal first that we went through. This one's similar, so it serves as a good review. This is transversal last. So the reflections are going to be in first A, then B, then C. And we'll follow a similar path, as it says. So O is the original. The reflection in A gives us figure 1. The reflection in B, parallel, gives us figure 2. And the reflection in C gives us figure 3. And the claim is that this is a glide reflection. So in order to specify the glide reflection, the most important thing we need is the reflection line. Because once you have the reflection line, it's fairly easy to construct the translation. So step 1, step 0 here, is just to show you what the reflection line is going to be. And its name is G. And I think once that line is drawn, you can kind of see the reflection and the translation, reflection in G and the translation parallel to G, that will get you from figure 0, the original, to figure 3, the final triangle. All right, how do we construct G? It's kind of interesting because it has to involve all three lines. So the method is this. You take the intersection of B with the transversal, the second line with the transversal, and that intersection is a point. So we've used B and C so far. And then you drop a perpendicular to the other parallel line, A, and where it hits gives you another point. And then you draw a line from that point, the intersection of D, that perpendicular, and A. You draw a line parallel to C, and that gives you the reflection line. And the question is, why is that true? So this shows you the algebraic trick that's involved. So remember, we go from right to left. This is reflection in A, followed by reflection in B, followed by reflection in C. And we insert between the first two a double reflection in D, which we couldn't have done, of course, without drawing that line. And remember, that line is from the intersection of the transversal with the second parallel to the first parallel, and where it hits is that perpendicular is line D. So line D is perpendicular to the parallel lines. And if we reflect in D twice, that's the identity. It brings you right back to where you started from. So you can insert a DD anywhere you want. So it's done here. Now the idea is to realize that now that we have more reflections, a reflection in A and then D is equivalent to a double reflection, we've shown, is equivalent to a rotation around the point of intersection of A and D, which is this point here. And then we have DB, and that composition of reflections is equivalent to a rotation around this point, the intersection of B and D. And the important thing is that the angle of rotation is twice the angle between the lines. So if you rotate the lines, the two lines, for example, A and D first, A and D are here, these two perpendicular lines. If you rotate those lines around their point of intersection and keep the angle the same as you do that, then the composition does not change because it's determined simply by the angle between, it's equivalent to a rotation of twice the angle between the lines. And if the angle between the lines stays the same, that is, you rotate both lines, then it's equivalent. And the same thing with over here with BD that we're going to do. DB, actually. D first followed by B. All right, so this slider shows that rotation. So I'll just go a little way and notice that actually B and D are perpendicular and D and A are perpendicular. So as long as we keep the angle as a right angle, and notice that there are two separate rotations going on. So there's these two dashed blue lines which maintain a 90-degree angle between them, and these two dashed orange lines which also maintain a 90-degree angle. And those are the images. And how far should we rotate? So watch B prime. We're going to rotate until B prime coincides with C. So the image of B coincides with C. So we're rotating the second of the parallel lines onto the transversal. And at the same time, that rotates A. Let's see. Wait, let's go back a minute here and see what's going on. Yes, that rotates A into G. That same, so that's, yeah, that rotates A into G. Because they're, yeah, let's see, I'm not sure. We just rotate until that happens. That's the easiest way to say it. Okay, so now if we look at the algebra, we see that AD, so watch AD here. Let's go through this again. AD, that's these two lines here, A and D, which intersect at this point. So AD rotate into GE. See? AD rotates into GE. So we replace the composition of AD with the composition GE. And similarly, excuse me, watch BD as we do this. So BD, so those two blue lines intersecting at this point go into CF. So B rotates into C at the same time because they're parallel. DB goes into FC. Should have said it in that order. All right. Now we have GEF and then CC. Well, a double reflection in the same line is the identity. So that's just GEF. And now if we look at that, G, remember, was the reflection line for the glide reflection that we're going to use. So first we reflect in that reflection line, and then E and EF. E and F are both perpendicular to that line. And so a composition of two reflections in parallel lines is equivalent to a translation whose vector is perpendicular to the lines and has twice the length. And the vector is shown here, the blue. And since this blue vector here, and since that translation is parallel to the line of reflection, this will indeed be a glide reflection. It's a reflection in G followed by a translation by this blue vector. And that gets us from the image from the pre-image 0 to the image 3. All right, complicated and very similar actually to transversal first. Now transversal second simply reduces to that previous case. So we reduce this to transversal last. So right now the transversal B is second. First we go A, then we go B with the transversal second, and then we reflect in C. But if we use this slider and maintain the angle between B and C, because it's first A, then B, then C, and maintain that angle, then that will be equivalent. And we simply rotate until the image of B is parallel to A. So now A, B, C, the new B, let's see, is that B prime? Yeah, I'm sorry. C goes into B prime and B goes into C, there. So, so A, B, C has been replaced by C, B prime because B went into C and C went into B prime. Let's check that again. B went into C. You can follow that. B1 is going down there. It goes into C. And A goes into, no, A does not go into. And C goes into B prime. C goes into B, excuse me. Let's see, C goes into B prime. C goes into B prime, we can see that. C on top there is now C1, and it goes into B prime. So now A, B, C is equivalent to A, C, B prime. A and C are parallel, so, and B prime is a transversal, so we've reduced it to the transversal last case, which was the previous one up here. Yeah, we've reduced it to transversal last, and we've done that. Okay, and that's the crucial thing. Now here's the general case in which we also reduce to transversal last. In this case, all three lines, no lines are parallel, so the three lines meet in three distinct points. But we are going to do the following. We're going to rotate B and C. This is a little hard to follow. B and C simultaneously around their points of intersection until B's image, so we're going to make two parallel lines, until B's image is parallel to A. So we're going to rotate B, B and C simultaneously around their point of intersection. So B and C are here, and their point of intersection is here. And we're going to rotate B and C simultaneously around that point until B's image is parallel to A. So watch the rotation. This time it's going to be clockwise. And B's image is going to be parallel to A. And so A, B, C is equivalent to A, B prime, C prime. A, B prime, C prime, but now B prime, A and B prime are parallel, and then C prime is the transversal last. And so we've again reduced it to transversal last. These checkboxes show the same construction, which is quite complicated, but we've reduced it to the same proof. And this shows the last one shows the reflection line, which is orange up here, and the vector, which is parallel to that line, which is this blue vector. And so we reflect 0, the original, in that line, and then translate it by that vector, and we get to 3. So that completes the proof. Here's just a quick summary. An isometry is uniquely determined by 3 non-collinear points and their images. We determined that. And then from that, we showed that any isometry is the composition of 1, 2, or 3 reflections. And then orientation helps here. 1 reflection reverses orientation. 2 reflections reverse it twice, or they preserve it. So the composition of 2 reflections is one of the isometries that preserves orientation, namely a translation or a rotation. 3 reflections has to reverse it, and there are 2 isometries that reverse, a reflection and a glide reflection. This is another example of why the glide reflection is added to the basic transformations, because of this nice symmetry. There are 2 isometries that preserve orientation and 2 that reverse it. And remember, the glide reflection is not just any composition. It's a very, very specific one. And it turns out to be very important because you can reduce any isometry to one of these 4. Okay, that is it for this lecture.